Kerbal Klassroom! Welcome to class. Today's episode is all about changing orbits. Okay, we're going to be talking about the nav ball and these different buttons, as well as the this maneuver node option. So I'm going to be switching to paint, but I wanted to show that there are these symbols, and I'm going to be using them. The prograde is the one going in the direction of our travel. The retrograde is the one going against it. Radial in is towards the planet. Radial out is away. Normal is perpendicular to our orbital plane, and anti-normal is perpendicular in the opposite direction. Alright, let's look at some stuff. Alright, so here is our orbit, and we're going in this direction as I symbolize with these arrows. If we fire in the prograde direction, so if we're pointing the ship in the direction that we're traveling and the engine's away, that will bring out the opposite side of our orbit from this to this. And this is the direction on the nav ball that you want to be facing. So if you use the ASDW keys and turn your ship, you can turn it towards the prograde, or you can click on the button to get to prograde, or you can click on the retrograde button and you'll get over to the retrograde direction. And if we are in our ship view, you can see I'm traveling this direction, and when I'm on retrograde, my engine is facing towards where I'm traveling. If I switch to prograde, then my engine is facing opposite, and the front of my ship is in the direction that we're traveling. Okay, and if we fire retrograde, we'll bring our orbit into a smaller orbit. It brings the opposite side in, and this is the symbol for retrograde. If we fire radial in, meaning if we put the ship facing the planet, then if you imagine that there is a vector symbolizing the magnitude of our kinetic energy and the direction, and the direction is always tangent, then if we want to burn this much energy to change our orbit, then our new motion becomes this green arrow, and it's tangent to this blue vector. So it brings the direction that we're traveling closer to the planet, and therefore we would be swinging closer to the planet over here. Radial out is the opposite, where if you're burning your engines towards the planet and facing away from it, this is the symbol for it. It rotates the orbit in this direction. If you click on the radial out button, you see that I am now facing away from the planet, and the radial in button, I'm now facing towards the planet. And the same thing is for our kinetic energy vector. If we're in this red orbit and the angle tangent to, or the vector is tangent to the circle, then if we apply this much vector, it will change it to this new pink vector, and that one's tangent to this black circle. So if we're doing a sideways view and we want to change the inclination, and you can think of the word incline like on the treadmill, if you raise the incline. So if we fire our engines down towards the orbital plane, and our ship is facing upward, then it's like we've brought up this red vector to be this new pink vector. If we fire downward, then we bring it down. And this is the symbol for anti-normal and normal. You can find them here. Here's normal. Normal, in this case, since we're in an equatorial orbit, is up. Anti-normal is down. Okay, the other thing is the nav ball is always pointing the orangish brown side towards the planet and the blue side away from the planet. And in our circular orbit, the prograde is always the direction that we're traveling, and retrograde is always the opposite, and those happen to match where the blue and orange meet when we're in a circular orbit. If our ship is facing in this direction while it's at this part of the orbit, when it gets over to this part, it will still be facing this direction. And when it gets over here, it will still be facing this direction, and so on, unless the ship has rotational energy. Now, if you do a time warp up here, you turn off part of the physics that would have rotation, and so you will always be facing the same direction. If you did have a little bit of rotational energy and you left it on the 1x time as it currently is right now, then you could actually keep spinning and you wouldn't necessarily face the same direction. If you have a target selected, these also can be used. We'll go over those in another episode. Now, if we're not on a circular orbit, the orange still faces towards the center of the planet. I don't think I got this one quite perfect, but this one's a little bit more accurate. It's facing towards the center of the planet. But the prograde is facing tangent to the ellipse that we're going. And so in this case, the tangent is not perpendicular like a T to the center of the planet. And so it's up here in the blue section. Up here, when we reach our apoapse, it is tangent, and so if we pointed prograde, we would be facing perpendicular to the, or we would be facing parallel to the surface. And when we're here, it's the opposite. The prograde is now in the orange section because it's pointing in that direction. Now, why do we have an orbit that looks like this? As we go up, we're losing kinetic energy, turning it into potential energy, and as we come down, we're turning it from kinetic energy into potential energy. And then as we're going this direction, we're being pulled towards the center on the x-axis, and once we reach the center, we've got our maximum velocity in the x direction this way, and as we come over here, the center in the x direction is pulling us this way, and so it's going to start slowing down in the x direction until it starts actually coming backwards. So if this is the pull of gravity, here's the pull of gravity here, it can be displayed in a y and an x vector like that, whereas this one has no x vector, and I didn't draw the other side. So the conservation of energy is the energy total is equal to the potential energy plus the kinetic energy. Now these units of measurement mean nothing other than I just want to show kind of a proportion. If the total energy was 10 at this point, it's still 10 at this point, and it's still 10 at this point. The only thing that will change it is when we start getting through the atmosphere and we have atmospheric drag. So I'm just kind of pointing to right above and right above the atmosphere here. Let's say the potential energy is 2. The potential energy is a function of your altitude, and your kinetic energy is how fast you're going. So you're going nice and fast here with lower potential energy, and when you reach your peak, you have most of it turned into potential energy. You still have plenty of kinetic energy. I didn't bring that to 0 because you've been sucked towards the center in the X direction as you've gone on this path, and then as you go over here, you're getting sucked in this direction. So you still have a bit of potential when you're over here, because you can still fall. And if you're in a circular orbit, anywhere you are, your potential energy and your kinetic energy is the same, and your velocity stays the same. So if you just did a fast time warp and didn't look at where your apoapse and your periapse was, and your velocity stayed the same the whole time, that means you're in a nice circular orbit. Okay, so let's just bring this out here and look at what we just learned. If we grab this, we're moving it forward in time. This is basically a planning mechanism if we plan to do a maneuver over here. So let's go ahead and do a maneuver right here. Let's bring up the nav ball by clicking on this thing. There's a setting to make it so that this automatically shows up in the map view if you want to find that. And so if we want to bring up our inclination, we pull up on this, and you'll see this orange new orbit. If you want to change it in a downward direction, pull it out this way, and this is the total delta V that you'll need to expend in order to get that new inclination. If you want to change, here, let me get rid of some of these. If you want to change the periapse and apoapse to be more like this, you can burn radial in right here if you wanted. If you wanted to do the opposite, you burn radial out. And if you want to bring the opposite side of the orbit farther out, you can burn that way. And if you want to bring it in, you burn retrograde. Now, I also wanted to show off one more thing. In the game, there is a good how-to manual by clicking on this little blue book with a rocket on it. If you look at the manual, I recommend looking at this nav ball page. It has a summary of what we just talked about and what all these different things are. And down here in the orbital maneuvers, if you want to look at shaping up, you can see that prograde will bring out to a new orbit. Retrograde will, that's farther out. Retrograde will bring the opposite side in. Burning normal and anti-normal will change your inclination. And burning radial in and radial out will rotate. The last thing I wanted to show was an efficient way of going from a lower orbit to a higher orbit in reverse, and this technique is called a Hohmann transfer orbit or maneuver. You do a prograde burn at your lower orbit until you have your apoapse at your target orbit, and then once you get to your apoapse, you burn prograde again, and you bring your periapse out to your new periapse, or if the orbit is circular, then they end up being the same. And then if you are starting from a high orbit and you want to get down to a low orbit, doing a retrograde burn so that you have this your periapse at your target orbit, and doing a retrograde burn at your periapse to bring your apoapse, this spot, down to this new orbit. Both of these are the same concept in just reverse, and this is the most efficient way of going from an orbit to another orbit. The reason why is because you're only changing the magnitude of the vector that is basically how much kinetic energy you have. If you spend time trying to tilt the incline or tilt the radial in and out, you're spending a bunch of delta V just changing direction and not changing the amount of energy that you have. So if you can just spend your time doing prograde and retrograde, that's the most efficient way of getting around. And here's a page about how if you did spend time trying to adjust your apoapse and periapse, but at different parts of the orbit, how much delta V you might spend. And we'll be going over orbit types, but just to have a quick vocabulary, if you're in a nice tight low orbit, it's called a low Kerbal orbit, or on Earth, low Earth orbit. If you happen to be going from one pole to the other, that's a polar orbit. If you happen to be around the equator, it's an equatorial orbit. If you have, whether you're low or high, if you have inclination, it's an inclined orbit. And you can have an orbit that's out called geosynchronous, which Kerbal has a rotational period of 6 hours. Instead of Earth having 24, they have a 6-hour period. If you're out at a certain distance, in this case 2,863 kilometers, you will have a period that matches the 6 hours. Take a peek at the KSpedia manual that comes with the game, and look at the orbital maneuvers section and the navball section. You can also take a peek at the section under the navball for more information on how to control your aircraft.